The tutorials, you can find them if you go to the website of the talk on Indico and press on Talk on Binder, and all the different tutorials should just open up. So the workflow in zfit follows 5 steps, always. We have a model, we have a data set, we of course want to fit that, and to do that we need a loss, typically a likelihood, or maybe a chi-square, which takes the model and the data, and then we minimize that if you want to have a point estimate, and we're getting out a result. So first here, we need to do some imports, and we'll look at data. So data in zfit is like a minimal part. This is not really relevant. If you want to do anything in data, use, as seen before, vector, uproot, pandas, whatever. But you can read data from anything like pandas, from root using uproot, anything. To define first, we create an observable. That's like this. We use a name, and we set some limits on it. And the space just defines like the observable itself. So we can now create some data, just some normal sample, NumPy, that's all compatible. As long as we're outside a PDF anyway, we can use NumPy or, but we'll see, these things are all a bit the same. They should all be able to be used. And we can just create our data set in zfit. There we go. We define observable and we define the actual data. This data set also has some functionalities like number of events or number of observables, and you can also have weights, but this is not like the main purpose of it. It's a very light container, let's say. We can also index it a bit like pandas data frame, like, so if you wonder what is this zfit data object, then I would say something like a pandas data frame, just a lot simpler, because all we need is to get it in and out of a PDF. And you can always say from pandas data frame or to pandas data frame. You can always go back and forth. Now, the model is the largest part of zfit itself. This is the, let's say, complicated part, and it's basically about PDFs. Now, that's a normalized function, and that is parameterized by different parameters that we want to fit later on. And a parameter in zfit, which we first create, just has a name, a unique name, and an initial value that we will use in the minimization, plus some limits, and we can also say step size that helps us with the minimization later on. And with that, we can create our PDF. And for starts, of course, we use a Gaussian PDF, which is simple. We just say what are the observables. That's the same we used before in the data. And what are the 2 parameters that we're having here. I mean, these names, of course, are different. It's just 1 to sigma. We can name a parameter, whatever we like here. Now, this PDF Gauss has also a bit of information, like how many dimensions does it has, what are the observable it's defined in, actually even the space that we defined before, and what is normalized, which is the same as the space. We can also access like what are the parameters. So this will give us mu and sigma, and tell us mu is this parameter and sigma of the Gaussian is this parameter. Now, this can be a bit more complicated, as we'll see later on. We can have parameters that depend on others, and that's why there's a second function if you ever want to retrieve all the parameters. So you're not really interested in like a specific parameterization of what is mu, what is sigma, but let's just on which parameter does the PDF depend, then get params. It's a nice function which just gives you set of all the parameters, and we can give some options here. So what does PDF provide? Yes?
Is a parameter boundaries mandatory? I mean, the upper bound for parameter.
Good question. Yeah, so technically it's not mandatory, because technically you can just give it a value, and if you remove that, let's say we do this, right? It would still work. That would all kind of work the same. However, it's highly recommended to give boundaries to document where the parameter should be, and also for any kind of minimization or something, because it tells the minimizer in which region it is. Boundaries in general, I would say this applies for any kind of fitting or statistics I do, shouldn't be meant as in a hard boundary, like make it tight, but rather as in, this is where the parameter really should not go over. So like in this region, we expect the result to be somewhere in the middle here.
So this is kind of the opposite direction of minute. Their recommendation is to not put any restrictions on the parameters.
Yes, exactly. Because the problem is you need to estimate at the same time well, it kind of agrees, because what they say is don't put parameters. What I would say, don't put parameters that influence the parameter. So if you put them far away, that's fine. Don't put them around your minimum. Put them far away where they really don't go there. But it helps the minimizer sometimes to know a bit what's the step size. So in principle, if you just have a starting value and a step size, that also helps. In general, I think it's just nice to have boundaries to say, well, what's the physical boundary? So normally we would say, well, a boundary should be a value where you say, well, if the parameter is there, then the result would be completely unusable. If you do a mass fit and your particle is around, I don't know, 5,000, and it's plus minus 10, if the parameter has a value of minus 1,000, something's completely wrong. So that's it. But an important thing is it should not be close to the limit. Otherwise, the statistical the statistical result is in there. This is free. So what does PDF provide us with? It has like three main functions, which is either PDF, integrate, or sample. So we can just use integrate, then we get an integral out over the limits. And what you notice here is maybe that we have something called TF tensor. Now, if you want to have something more on tensors and TensorFlow and how all these things work together, there's an extended tutorial on TensorFlow. You can just click here and it will get you there. A part of that, it's like NumPy arrays. You don't think of anything special outside, just think that this thing is a NumPy array. It even gives you the answer here. Why I'm saying that it's like a NumPy array, you can, for example, do NumPy to the square root on that value, and it gives you back a NumPy array with the square root of it. So think of NumPy array. We can use sample, and if we use sample, then we're getting back some data. The same data as we sampled before from the Gaussian with NumPy, we can also just get while using the zfit PDF. The difference here is notably that sample is now just within the limits that the Gauss was defined in, while usually NumPy and so on, they just do like a full Gaussian and the limits are minus and plus to infinity. And again, we can just get values out of the sample by saying which observable and that. It's a bit like Pandas syntax, as I mentioned before. The sample, of course, number of observables, ops, the same thing. And the third, probably most important method is the PDF method. And that means, of course, the normalized value of our PDF. We can just give in sample, or we could give in anything else. All right. So we have a PDF, we have data, and one of the things that we can do is, of course, plotting. Now, for plotting, zfit again relies heavily, as for many other things, as I already mentioned, on the whole Scikit-HEP ecosystem and the whole Python ecosystem anyway. So plotting, of course, should be handled by different libraries. Now, this is an example. If you want to have a plotting function, we can just get the lower and upper bounds from the data limits. We can do some linspace. We could also use NumPy linspace. We can get the model be evaluated at PDF, normalize it right and stuff, and then plot it. And for the data, we can do something similar. We could use any kind of plt.hist, which probably was the way to do it in the past. This is like the primitive way, but there's also a more modern way, which zfit has. We will go more into this to binned with number of bins. So we have a binned data and we can directly plot that. So plotting the model and the data looks like this. Quite easy and straightforward. Of course, we can do this more sophisticated, as we'll see. Now, we've seen a Gaussian so far, but zfit offers a whole variety of different models. This is the list of them, and you can also create a lot of custom models to be spoiled for later. And there are some additional ones in physics that are specific to physics. If you want to know for example, more about KDEs, and there are specific tutorials. So we can now create a zfit with like 3 components, an exponential, a crystal ball, and maybe some partially reconstructed background on the left using a kernel density estimation. So if you want to do this fit, we create again a different observable. We call that mass now, and we create now a crystal ball function. Mu, sigma, and all as before. We create the combinatorial background, and we create our KD1 dimensional. Great, that's just an improved version that also works for large-scale data. I mean, notice we have here 70,000 events. So using just a normal one will probably be a bit computationally intense. But there are a few optimized versions in KDs. Now we can compose the models. What we want to do here is just a mixture or a sum PDF. If you want to know more about how to make composed models, for example, also if you want to have products and make them multidimensional and everything, there's a tutorial linked here, which you can also check out. For the model, since we make a sum of 3 PDFs, we will need 2 fractions, because the fraction is the last one is 1 minus the others. That's why we create 2 signals here. Maybe note we could also just use technically constants if you're not interested to float these fractions. And as also another side note here, you can use also 3 fractions if you want, but then you need to kind of control that they depend right on each other. So one's feature, but you can if you're interested. Now, we want to sample from this example to do some fits to it. And we can use a small trick here that for better or for worse, parameters in zfit have a global state. So we can set the value temporarily, and it will give us a different value and then set it back. And with this useful trick, we can create here a sample. We can just set it to certain values. They're all set to these values here, and then we can just create a sample of 10,000 points. So now we have a model and we have our data, and that has like, that currently looks like this. So the model, the data when it was sampled had different parameters than the model now. Now, what we can also do, of course, plot all the distributions. That is rather simple because model has an attribute. That's the sum PDF, which is called PDF. So we get all the PDFs and it gives us all the fractions. So this is basically enough. We just go through each PDF and multiply it with the fraction, and we get the components. So plotting all the components as well, and the main one is like this. Simple, straightforward. So model has, as I mentioned before, has all of these frac parameters. They're also used in multiplying things. Now, one thing we didn't touch on yet is something called extended PDFs, because often we're not just interested in, let's say, normalized to one PDF, but we're also interested in an overall yield in the number of events in the data set. Now, there are a couple of more details, but in general, an extended PDF is like a normal PDF in zfit. The difference is merely that you can do additional things. For example, you can do sum without actually giving the fracs, because it will automatically take the yields of different components and add them correctly. One way of creating that such a PDF is just using this syntax, saying create extended, and we get an extended one with the yield also parameter here. So having all of these extended PDFs here, we can go and create a sum PDF of the 3, and you see this is all the same, but now we're not giving any fracs. And the model itself is now also extended, the sum, of course, of these models. Now the loss. That's the third part in zfit minimization. We can create an unbinned negative log likelihood using our Gaussian and the data normal that we got from before. So loss as well has some values, like some attributes like a value, like that just calculates the value of it. This is just a negative log likelihood. We can get the gradient out if we want. We can say which parameters, and we can get the model and the data or possible constraints. And we can also get all of the free parameters. Note that this is only mu because before we said in the very beginning that sigma should not be floating. So this won't be seen as a floating one. And if you say get params, we could say here which ones we want, but by default it just gives us the floating free parameters. Now, if you want to do an extended likelihood, there's a difference. Unbinned negative likelihood is just fitting us the shape of the PDF. We can also do an extended unbinned negative likelihood, and that takes into account the yields of the data and of the model. But it's the same game, and the difference here is that we don't just have mu, but we also have the different yields that are floating. So fourth step, we want to minimize this likelihood. We could already plot it, we could do things with it, but we want to minimize it. And therefore we can use the great I-minute minimizer. There are other minimizers available actually, which we just create like this. Minimizer equals zfit minimize minute. There are other minimizers like the whole NLOpt and SciPy and IPyOpt and so on. But there is one problem, and that's like the when to stop. So it's not so easy for a minimizer to know when to stop, and I-minute has a very nice EDM, estimated distance to minimum, that is quite reliable. So this is, I think, the best thing to do. Others, if they use the same, that they currently use the same in zfit, they just have the issue of being very slow in calculating that in the end. So we can still see what is like all the parameters here, they're all standardized, and what are all the different minimizers available technically. But I think Min is usually the best one. Now, as I said that, as a side note, as it's well integrated, we can also directly use I-minute out of the box to minimize the loss, and we don't need even like further zfit here. So we could just do that and use minute directly. And if you want to use zfit, as like here, we'll get back a result. So this is the I-minute. If you just use pure I-minute result, we could just use that and we'll get back whatever I-minute gives back. Or we can, of course, just use directly zfit itself and then get back a result and plot the whole model. There we go. That's the fit. Now what we got here is the result object, and the result object from zfit involves a couple of things. So on one hand, we can just print it, and it gives us a nice overview, whether it's valid, whether it converged, what's the estimated distance to minimum, what are the values, and so on. On the other hand, we also can directly access the parameters at the minimum and also print them. This is like a bit dictionary-like, which we can access, for example, like this. And we're getting back all the information that the result knows about this parameter. We can access the fmin, and we can even get the original min-weight minimizer that was returned here and knows all of these things. So you can access all the original I-minute information, you're not losing anything. The nice thing is, a part of this very last piece, all the things are also available with any other minimizer. And that is crucial, for example, here, if we go about estimating some rough uncertainties, like Eschle, that I-minute has, we can just call now result.Eschle, and it will do the hashing calculation by default, actually, with I-minute itself. We can also switch the methods as shown here, or specify them. There's an independent implementation in zfit. And the same works for any other minimizer that you use. And now this has been added to the params. We see here hepstats uncertainty on it. We can also do some minus uncertainties. It's called errors. And there's also a zfit error here, which is the same thing, but just with pure zfit. Now, there is something called new result here, just that you're not confused, because this does some kind of profiling. It means that it could find a new minimum, and this would be this new result. And here we get now the whole result again, printed out with the errors, asymmetric errors added for the things that we wanted to have. Now, there's also covariance matrix available. Now, this is basically the end of zfit, and there's a small bonus here that's still a bit experimental, and there's an extended tutorial on it. Yeah, Alex, you have a question?
Yeah, I was wondering, because you showed the plotting of the result, does this also include visualization of uncertainties in some way, like error bands and such that you get from propagating your post-fit uncertainty through?
Not really, but you can do you mean like the uncertainty of this result here? Or you mean the plot itself?
Yeah, propagated to the plot. So effectively having like a sort of the best fit thing here, and then also some band that indicates the uncertainty in the best fit.
Yeah, so there's nothing by default provided in general. Also, this plotting function is just defined here, so it's like meant to be done by the user or by a different library, maybe NPL-HEP or something. But it's, let's say, quite easy to just do that. Change the parameter by 1 sigma or something, and just plot this. I mean, this was like defined here, I think. Yes, this is the normal plotting function. That's all there is, and then you can have like this, exactly this one here, which just plots all of them. So you can just like extend that easily to plot. The idea being that zfit should focus on like minimization and giving the uncertainties and not go too deep into the plotting. But all the information is there to easily do that. And there are if you really want, we have maybe some routines around from analysis and so on that do more sophisticated plotting, just not built into zfit. So what we can do here, this is a bonus and it's a bit unstable, so it still can fail for some more complicated models that we don't support it. We can also go to serialization, because one of the things we want to do in the future, the longer the more, is to serialize our model. So we can do the whole model as a dictionary representation, which tells you, what's the type of it, what's the name, what are the PDFs in there and stuff. That's a lot of text, so we don't need to go through all of it here. And it has some stuff as well that looks like binary and stuff. So we can also do it to YAML, and we're getting a nice YAML representation, for example, of a Gaussian. We can save it now in a file, and we can also load that again. We can also do this with our likelihood in the end, and we get all these additional things, and we can even get our data in there. So with this, if that works and doesn't fail, you're able to publish, let's say, your likelihood, if it's not too complicated, directly with the paper. And you can also reload it. Since it's still a bit experimental, it means that it maybe fails. There are still some hiccups in there. And getting out of zfit now, we can start with hepstats, because if you want to do something more on errors, for example, we can use hepstat. So hepstat is there, it's built on top, while zfit just builds the model mainly and is able to minimize them. Hepstats can do confidence intervals and throwing toys and stuff for you, or calculating sWeights. Now, if you want to get, for example, a 68% confidence interval on the mean of the Gaussian that we got just on the mu, we can just import the necessary things. That's on one hand, the confidence interval calculator. The hypothesis test, and we can get the asymptotic calculator. There's also a toy calculator, which actually throws the toys. And there is a POI, a parameter of interest array, which contains all the different values. So we can just create calculator directly using the result of zfit, and also specifying minimizer that should be used internally. Now, getting the value and the errors around, we can have a scan, so we can say which are the possible values that you want to have scanned, and with the confidence interval created using the calculator and the POI array, we can then calculate the different intervals that are valid, and then we can plot them. This looks a bit more sophisticated. Maybe that's more what do you thought of, Alex, as well? And this is just in a utils package here in let me show that quickly. That's just plot limit here, a bit more sophisticated, something that doesn't like fully fit into a notebook. Okay, while that's plotting, it's run local, so my laptop is a bit unyet. Are there any questions to the introduction part before we'll go and continue with the bin fits? then we'll just move on. Is there anything in the chats? Okay. So binned fits in zfit can be done as well. zfit is started out with unbinned fits, but the idea is that it can do any kind of binned fits. Now, the binned fits are probably perceived as two things. On one hand, if you fit unbinned, but you have a lot of data, you may want to do a binned fit of an analytic shape, often done in analysis B or about 2, for example, or you want to just stack templated histograms from simulation and fit binned anyway, which is often done in CMS and Atlas. Now, if you want to do a template that fits with, let's say, some very strong restrictions in a way, like irrelevant binning and no analytic function components and morphing and so on, the hist factory model, then there's PyHF. PyHF will also have a talk here, and they are doing that very highly efficient. So it's a very limited model, but it's the probably most used case in Atlas and CMS and certain types of analysis. So they're really specialized in this analysis. And while technically you could reproduce it with zfit, it's quite inefficient. I mean, you could reproduce everything just using pure assembly or at least NumPy. But the idea is that zfit can do anything that his factory can't. If you want to do weird correlations, if you want to have analytic shapes mixed with binned shapes and numerical normalizations and whatever fancy things that don't work there, then you can do that. So there's a small guide here how to choose your fitter framework. Now we can do all of the imports, and the binned fits in zfit look very similar. There is just something like called a binned sum. There's data, there's a binned data, and from unbinned negative log likelihood is the binned negative log likelihood. So we can again create the same thing, for example, before we now start from like going from the unbinned to the binned, but we can also start, as we'll see, directly from the binned part, of course. So we can just create again our Gaussian data and then unbinned negative likelihood. So far, this is all the same, and we can also use again minute to minimize, get a minimizer out. Here, while we just use the zfit provided gradient instead of the internal one as before. Sometimes the zfit one is better. That's like in the analytic one. Sometimes it's the minute one. That all depends on the use case. Just try out. Now, if you want to make all of the things binned, we want to get binned data. We can just say data to binned. We can say model to binned, and we can create now a binned loss. And now, as before, these 5 steps of zfit are quite independent. We just minimize our loss. It's not just a binned loss. And we can do uncertainties again, and we can also do minus errors, and we can print it again. Pretty much the same game as before. That went quite fast. So let's look at the bin part in a bit more detail. So what we got out is some binned space, and this is now, if you're familiar with like hist or boost histogram, if you're not familiar, I highly recommend to check them out. But if you're familiar, they're very similar to the axis there, to the regular binning or something. They're basically designed after that. We can also just convert them explicitly, and you see we have regular binning and variable binning. That's basically the same syntax, and that's also very compatible, as we will see soon. So as seen before, we can just convert data to binned. The model, we can also convert that to something binned. You will probably recognize this depiction if you're familiar with hist. So zfit is fully compatible with the UHI, that's the Universal Histogram Interface, and that's what many libraries like histogram, MPL-HEP, boost histogram, and so on stick to. So this is like, you can just directly use a histogram, for example, and you can convert things back and forth. For example, if you have a model in zfit, binned model, you can just say to hist, and you're getting your hist out. And that means you can do all the things that you can do with it. You can do counts, you can do variants, you can do values and stuff like that. And same for the binned data, just that the binned data itself already sticks to UHI, so that is already a histogram-like object, which has counts and variances and all of these things. The binned PDF has the same thing as the unbinned counterpart. It just has like 2 other things, which is counts. There's the number, the absolute counts in the bin, and the relative counts, which is just like normalized. to the total number of counts. The difference between a histogram like hist or binned data in zfit and a binned PDF is that a binned PDF is parameterized. So it's a function of something. And we can also create, as before, a binned sample, just using sample, but now from a binned model. The plotting gets a lot easier. I mean, it wasn't so difficult before either, but it gets easier even by just saying now mplhelp.histplot, and histplot expects a histogram or something that is UHI-like, but the model, the data already is like that, and the model we just call toHist, and we may scale it up, and we can just do the plot data model. There we go. So we can plot counts, or we can plot the density, whatever we want. Now, for the binned was, we do have the extended unbinned and the unbinned one, but then we have binned negative correlative and extended binned negative correlative, the Pondo, the direct equivalent to the two previous ones, and then we're having an extended a binned chi-square and an extended binned chi-square. So we can also just do chi-square fit with it. So we've seen before how to get like binned PDF and binned data from an unbinned one, and how to minimize that, but we can just use directly histograms. So we can create hist PDF directly from a histogram. And we're getting the counts, and we get that. Now we can also say, what's the yield actually of this histogram? And so it just takes the histogram as the shape. Let's say we're getting a histogram PDF that has now a total count of 40,000, because the yield of it, here given with extended equals, was defined to be exactly 40,000. And now we can go into the whole fun of bin fitting, which is, so we can say we have 50 bins, and we can create now bin-wise scale modifier. So we sometimes want to vary all of the bins a bit, doing something like Beast and Barlow or Beast and Barlow Light. Different here to something like PyGEF, we need to implement the things manually. But the good thing is we can do whatever we want. And for example, we can just give the hist PDF that we created before here and say, well, create modifiers, and it will create modifiers ourselves. We could also just do them manually and just create 50 parameters ourselves, and then give them to the binwise scale modifier. Or we could do anything, as long as it's 50 entries. These can depend on other things. It can be constant, they can be whatever. The modifiers themselves are now a large list of parameters. They're just here to scale up and down things, and so is the yield, which is just dependent on these parameters. Another funny thing to do is morphing. So the idea of morphing is that we're having different templates generated with different parameters. So we have simulation, and we change some parameters, the energy scale or something like that, plus minus 1 sigma, or zfit plus minus whatever sigma you want. And then we can interpolate between these templates and have a parameter that controls interpolation and constrain this parameter and say, okay, it should be around this value, but plus minus 1 sigma, Gaussian constraint, it can also be the other one. So we're not really fitting a fixed template, but we have a template that can vary. And that's called morphing. So what we're doing here is we just create 4 different templates for these different values. Normal is plus minus 1 and the 0, but you can do anything in zfit. You can also use minus 0.5 if you know some more information about it, whatever you want. And then we create alpha that is meant to say where on the morphing we are, and the background yield. And with that, we can create our background PDF with a spline morphing PDF that takes alpha, the background hist PDFs that we just created, these 4 here, and say that it's extended. So to give you an idea of a plot, we can just plot that. Again, we set alpha to a certain value, just plot it, and plotting is really easy because we say again that to hist we get it. If you want to do a simple fit, we can also just use this, and then we don't do it. And now we create a bin sum of the signal PDF and the background PDF, and we convert it to hist, and automatically it will give us a nice display of the model. We can do the same trick as before, sample some data. This is the data we look for. And now we're adding our constraints. Constraints here mean additional terms that limit, it's like additional knowledge that we're incorporating into the likelihood, and that will limit how things vary. Because we said these bins can scale freely, so that means we want to say, okay, there should be around a certain value, for example, using a Gaussian constraint and specific uncertainty. Same goes for alpha. So now doing a binned log likelihood fit, we can do it again using minimate that we created before. And once we have that, we can just print the result, which, yeah, this was automatically created. That's why the names aren't so nice of these, with a lot of free parameters. But of course, let's just plot them because that's easy and nice. And there we go. Looks quite reasonable. And we can also get our yield, which is a composition of many parameters. That's why this looks so funny, let's say. And as well, we can do errors, or we can do Hessian. We can also do it for just like a couple of parameters, signal yield here and alpha, for example, instead of doing it for all of the 50, because doing it for all of the 50 parameters can take quite a while. Even like this, it's just a lot to minimize. Now, we can go back and forth of, here we're getting in now. We can get back and forth of binned and unbinned PDFs. We've seen how we go to binned, but we can also just go back to unbinned, for example, by doing some splines. So we can take our signal PDF, that is the background of the signal from before. The signal is just a Gaussian, and we can put it spinned, and we can say, well, make a spline PDF out of it, and we're getting an unbinned spline. So we're back, and we can plot the unbinned spline PDF, just like this. We see now this is the data that was, this is the signal PDF that we say to histogram, and this is the unbinned spline. So this is the same, but just splined. Now, we can create their signal, but we can even, just to mention that, we can even just say, so therefore we need to look at this line here, instead of making a sum PDF by using our unbinned spline and the background exponential, that is unbinned, we can use signal PDF directly. This was the binned one, and say to unbinned. So it's still binned, but it's now an unbinned PDF, just looking binned, and the background exponential, which will become clear once we plot it. So we see both have a background exponential unbinned. One has been splined, that's why it looks so smooth. The other one is just still the same binned shape, that's why it looks so edgy. And now we can again use the same thing with hepstats. So this is the whole basic, and I think these things are what makes zfit. You can go a lot more complicated in each of these. And depending on your time and interest, things to look at, I will just introduce the other two tutorials that are here, which give an advanced use case, but you can go through them then on your own. A central part of zfit is that you can create your own PDF. And that means that you can create, for example, your own Gaussian like this. So you can just inherit from a specific base class. There are two. This is the bit easier one, but there's also a more advanced one, which is just shown below here, the base PDF. You specify how many observables you'll expect, and you'll see the parameters. We can name them median standard, whatever. We can have as many as you want. Then we overwrite the unnormalized PDF. We're getting our observables. We get the parameters, and we can just formulate things. Now, the important thing here is that inside we should use ZNP. This is like NumPy from zfit. We could also currently use directly TensorFlow, but that may change in the future. So just use this, which is NumPy-like. And I guess the syntax here should be clear. Now, this maybe looks very minimal. It's like, well, what have we done so far? This is not the end of the story, right? But the good thing about zfit is that this is already enough to have a full function PDF. An alternative, but that's already advanced, is to do it this way, but we'll not go into this. So we have this class myGauss. We can also just re-execute this, so you know that we're using the upper one. And what we do is, as before, we can create like observable, we can create data for that one. And now we create an instance of myGauss using a main, using a standard parameter. By the way, now without limits, because we can do it without limits too, that works. It also doesn't have to do with floating or not. That would be this. It means it's not floating. And we're getting Gaussian. And with this, we can do all the same functionality that we could before. So we can get probabilities out, or we could do .integrate, .sample. And the question is maybe how to do that. zfit integrates and samples numerically if nothing analytic is available. But additionally, you can also have an analytic integrals register. You can override all these functions. So if you want to do something a bit more advanced, then there are guides, as mentioned in the beginning, where you can see how to do this at once. But the core thing is, this is all it takes if you know your shape to implement the new PDF in zfit. And so this is where we can really step up the game, and that means why not go multidimensional and do an angular analysis fit. For example, we can just go and see if we want to do a certain fit in physics and estimate the number of signals that we expect. Take the shape, for example, an angular analysis of B2K star LL, the case from a paper, that's public paper, and just implement it in zfit like this. Now, that looks already a bit like a beast. We say these are all the parameters. We're getting the parameters and anything, but this is just a bit of multiplication, a bit of cosine, sine, just directly taken from a paper. Now, that's all it takes in zfit to do your own PDF. You can also do a lot more complicated things, build your amplitude, for example, with the PWA project, and then you can also use zfit to directly fit them. Whatever you want inside here, as long as it's ZNP or TensorFlow or something like that, then it will work. So let's define this one, and then we can also create the multidimensional space. As we've seen before, we've done these one-dimensional spaces. And we do the same, we just create 3 of them in the right order as it's given here. And then we just multiply these, and we're getting our angular observable, just the product of these 3. For parameters, we can just use plain dictionaries to create them, to manage them. I mean, Python is super nice in this regard. And we can use this angular PDF like anything else. We could also just, for example, multiply it with my Gauss, and then we will get a 4-dimensional PDF. Just works out of the box. It's a PDF. It can be multiplied with out-of-the-box PDF of zfit or with your own or anything. And it also means we can do integrals or samples and getting the probabilities out of the angular PDF of this whole thing here. And we can also just build now an unbinned negative likelihood and a PDF and a sample from the angular PDF. And we can now just fit that. We can get the results, we can do Hessian, we can errors on it, we can do toys, whatever we want, and we get already a nice estimate for our fit. This does take a bit of time. That's because it needs to do the normalization numerically. But we see it starts, and we have set here robustity equals 7. That means it prints out a few more steps. It's going to take like 20 seconds or so. And the last thing to guide you to is this, let's say, more real-world example, which is about combining measurements. So what we're doing here is we can just create our rare signal. We have 120 events. We create, as before, some data. We create some observable. We create some data. That is a combination. And again, as before, we create our Gaussian with all the parameters, exponential. We can create some of it. And as already mentioned before, we can create a constraint, Gaussian constraint on mu that is used in the signal here. We create extended unbinned negative of likelihood, and we can fit that. Well, so far so good. That's the normal example. As we've already done before, we're getting out our result. Now, sometimes we want to do a simultaneous fit. We don't just want to fit one thing, but we want to fit multiple things at the same time. In this case, the example is that we're going to fit something resonant that has like 40,000 events in there. So that is a lot more pronounced as a peak. And then we can just, this is the guide on how to share parameters, but basically it's just if it's the same parameter, it's going to be the same parameter. So here we can just kind of have the same, some of the same parameters shared. I'm not going into detail, it's just the same model building as before. And while technically it's just a product of things, what we can do in zfit is we create our rare negative log likelihood with the model, the rare model and the rare data, and we create the resonant model and the resonant data. And then if you want to do a simultaneous fit, this is technically just a product of likelihood. So we just create the product here and we're getting it out. But this means, and we minimize that. already minimized, we can do hash, and then we're getting the result. Now, these both things have been fit. Signal and background have been fit, so we can now plot it. And plotting it, I've sometimes got questions like how to do that, but this is like very straightforward because it's just like plotting that one-dimensional gauge that we had before. We just have another one that has been fit at the same time, but there's nothing two-dimensional or anything about it. So we can just do that. This is the rare mode, and this is the resonant mode. You can go do it yourself, but it's just the same thing as before, plotting them individually, basically. I mean, as we see here, it just goes through the models of the fits, of the log-like layers. Now, just to prime you, we can do, for example, a discovery test using hepstats. So this will give us a nice plot to see if it discovered something, and if it didn't discover, we can also do the upper limit calculation, so we can see what's the upper limit for it. I'll just skip that part, it takes a bit of time, but you can just do it. And the last thing that I think is also nice to mention with hepstats, and there's also an explanation on it, is sWeights. This is if we have two-dimensional data set. This is one dimension on the left and one dimension on the right. This is a variable, and we want to get this pure signal here out. What we can do is we can fit this part here, and then we can use sWeights to just disentangle these with weights. Now, in zfit, we just do the same thing. We data extended unbinned negative of likelihood and minimize and all the same things as before. And this is the fit to it. And then using the sWeights is as difficult as importing it and saying compute from the model that we just had and the data. Then we get the new weights. And with the new weights, we can apply them. And what we'll get out is this one here. So this is like just illustrating the weights, but this thing on the right is now the weighted histogram. So this is what we've seen up here. And everything else, the background is statistically removed. This only works if it's uncorrelated. If it's correlated, it would look very weird. All right, this was an overview of what zfit can do, what hepstats can do, and embedded into the whole ecosystem. Any questions or things that you would want me? I think we have, if I'm correct, like 10 more minutes, which I think we can use for questions or for understanding, or if you want to have something more. Yeah, Alex?
Yeah, thanks a lot. This is going to be not directly connected to this, but like I'm broadly more curious about zfit. Has anyone looked into using this in sort of end-to-end automatic analysis optimization context with like passing gradients all the way through? And specifically, because you already have, like, you can auto-diff like some pieces here already, can you also, for example, hand over accounts of data or so, which are already coming out of a tensor? So you could imagine propagating back from your very final output to things that happened previously?
Yeah, that's a good question. A bit advanced technical, but it brings a very good point that zfit inside can already, I mentioned this with using gradient equals zfit. So yeah, it uses all the power of TensorFlow and the future most likely checks to automatically create gradients through, let's say, everything through the whole likelihood. In terms of passing things through, I think no one has ever tried it. I think the problem is sometimes with the minimum, and I think in the way the analyses are done, it's usually people, I think, so far are at least the ones that I know and that I talk to don't have like the rest of the analysis really straightened out like that. So they use just different means of optimization. They can't have cuts and stuff yet in, although I'm aware there are, of course, libraries that can do that nowadays. But it's not so. It should be doable with a few tweaks, and I think this is absolutely the goal for like version 2 that we go to. That this is a doable thing, because yeah, the gradients, they should go through. They can also be retrieved now. Actually, if you say nll.gradient, you get the gradient directly out. Yeah. So now it needs a few tweaks probably. No one has, I think, really tested that, at least not that I'm aware of. But this is very much in the scope of things.
Okay, thanks. Yeah, that's great to hear. Indeed, like I can imagine that when trying this out, okay, there might be some things people run into. At least we've seen this in other cases where things that should work on paper, there's okay, some edges, but like those can be fixed. Very, very nice to hear. Thanks.
Luigi? Yes, let's go ahead.
Hi, can you hear me?
Yes, I hear you fine.
Hi, Jonas. Yes, very nice tutorial. I learned many things. So I've never used zfit, so this might be maybe a, let me say, a question, you know, being asked many times. I was wondering about in general the performance of all these things that you showed us and how it is implemented back behind the curtains. I was wondering whether all of this is, for example, NumPy based. Do you implement any, let's say, further optimization or acceleration mechanism? How much, let's say, performance in general is a problem, and how much do you rely on other libraries, other tools? You mentioned something when you talked about PyHF and the performance there. I don't know, can you make some general comments?
Yes, that's a very good question. I think it's nice that you ask it, because I may sometimes forget the point. So I think also historically, zfit was actually created, I think about 5 years ago-ish, with the idea of having, you know, not just a nice API that can like integrate well into their libraries, but also that it's performant enough to be in Python. Back then, people would say, well, Python, that's too slow for a fitting tool. And basically, zfit and PyHF both kind of started out and said, well, I think we can do faster using some techniques like TensorFlow. And so this is a very like essential part actually of zfit, that it delivers high speed. So having a nice API integrating fully with the Python world and being easy to use, plus having the high speed behind the scene. So what zfit does behind the scene is it relies on, it doesn't use just NumPy, but it relies on something like TensorFlow, which you may know from neural networks, but it doesn't do anything with neural networks, or JAX. And what they use is something called JIT, so they have just-in-time compilation. Now, what that means is, that means that it's kind of the Python code is just run once or twice in the beginning, but then zfit will run significantly faster to do the calculations again. So that means, because first time it compiles it, and that needs a lot more time, but then every consecutive call is quite fast. That means on one hand, the attention has to be paid. That's why we need to use here setNP and not quite NumPy. Now, side note here, if you want to use pure NumPy, you also can do that with zfit. You just need to tell him basically set graph mode false, but this should all be more explained in this tutorial here. And there's also like TensorFlow and how to use custom code in zfit with the thing. So it uses significant speedups inside. That's like, compared to NumPy, that can be a factor of 10, 100, 1,000, 10,000, depending on what it is. And it means it can also run automatically, not just on multiple CPUs, but also on GPUs. If you can install TensorFlow and see if TensorFlow runs on GPU, and that's, you know, there are many instructions on that. If TensorFlow runs on GPU, zfit will run on GPU. So that goes very automatically there. And that is in terms of speed. So since you asked that, also in comparison to RuFit, and well, in RuFit there's got some updates, and they have some presentation even now. I also talked to the guys in terms of speed and so on. And I think overall, I would say they're on a similar-ish scale. If you go for smaller fits, if you want to fit the 100 points with the Gaussian, RuFit is going to be a lot faster. But that's on the millisecond level anyway, and that's not the point. You know, at least that's the philosophy of zfit. You know, the small fits, that's great. If you go for larger fits, I find very different things. So sometimes RuFit is faster, sometimes they're like equal-ish, sometimes even zfit is faster. It really depends on what, because I think that the difference is a bit, zfit tends to be a bit slower in terms of overhead in the beginning and so on, and has, though, for large fits and complicated fits, zfit, since it uses behind the scenes something like TensorFlow, that can optimize very nicely away sometimes constants and things, including it can get automatic degradient. So I think it really depends there, but so far I found personally and people that there was not a significant difference. So I would say usually if you have one fit in zfit and one thing in RuFit, except for extreme cases, they're within like an order of, you know, 10. Order of magnitude of factor of 10. Maybe, you know, maybe it's a factor of 10 slower. That could be in the worst case. So I think it's usually not a relevant thing, especially for large scale fits like amplitudes, which you may want to run in a GPU, for example, or something. I find that it's like very comparable usually.
Okay, thanks. It's really great to hear. Thanks.
Do we have any more questions? No, I don't have any specific myself, Jonas. Been following the project since a while. I saw lots of interesting new things actually that I was not aware, especially about the binning world. The bin world with bin fits.
Yeah.
That's very nice to see. I know that certainly 2 years ago that did not exist, and then some developments, and now we actually have something is in production. So that's very nice to see. Since we still have 2 or 3 minutes, do you want to make a comment? Do you have any news on this standardization of workspaces, so to speak, and how to store the information and pass it on to other people across different projects? So whofit, PyHF, zfit, and so on.
Yes, I think I do not have too many news recently. I've been myself quite busy just with some stuff, but I think it's good to mention, because I didn't mention that here. Thanks that you actually mentioned that. So when I set this like HF3 thing and deserialization here, this is not completely random. This started out that we need some kind of serialization and workspace, of course, but the idea here is to have this format shared. It's called HF3 for a reason. You can also click here and you will be on the HF3 standard side, which is like a kind of working group, and that should be standardized between like zfit and rowfit and PyHF and even others. There's in Julia also a framework that does some Bayesian inference and so on. And the idea is even to get like also some data format just to basically serialize our statistical models. So zfit is like not 100% compatible because, you know, we're going to a standard. So you see, oh, this has to be implemented a bit differently than that, but it's very much going there. And for zfit v2, which is just going to be worked on now-ish, this should be like then fully compatible. So rowfit has also HF3 in there. It's not 100% compatible but for something it is already, and very close. So keep an eye open there. If you have inputs on that, or if you yourself think, oh, a data format should be specified there. I think some experiment, CMS, I think recently, they made also responsible to make sure that their internal serialization is as compatible as HF3 as we are and so on. Then also just get in touch with us, because it should be a standard that covers, let's say, the statistics that can serialize the statistics in HEP.